Hello everyone, let's study what exactly the convolutional code. In this particular session we are looking at exactly the convolutional code, their advantages and how it is implemented, what are the different representation techniques for the convolutional codes. Okay, let's proceed with the introduction of the convolutional code. This code actually first introduced by Elias later on with the Viterbi. It has been further modified and that is to for the purpose of decoding. So that's why it is also called as a maximum likelihood decoding. So Viterbi actually provided a good approach for decoding of this convolutional code in 1967. Now let's look at what exactly the format or the convolutional code encoder, we can say the circuit. Okay, so this is some kind of format for the convolutional code where the k input bits will be taken and based on the number of memory elements n will be the output bits. So this is the format called as a n comma k comma m. So output will be totally depending on the current set of k input bits, as well as we can say that it is nothing but the linear circuit sequential circuit with the input memory m. So whatever the input memory blocks we are using, that is represented with the you can say the variable m. Now what are the real advantages of this convolutional codes? These are the codes with the low latency. This can be with the good performance by expanding their memory depth. Means we can expand how much memory blocks we are using in the current encoder. This can be further extended. Next thing is, as far as the applications are considered, these are applied in applications that require good performance with low implementation cost. So cost of implementation is very low because it is totally depending on the memory elements, nothing else. Now let's look at what exactly the encoder representation, how we can represent it, which are the different representation techniques. So these are the encoder representation techniques, in which the first technique is state diagram, second is the code tree diagram, the third, that is what quite importance as far as the exam is considered, that is called as a trellis diagram. Okay, this is quite important. And the fourth one is there, but which is right now not mentioned over here, that is the polynomial representation. So that is the supplementary kind of representation apart from these three. Now let's look at how we can proceed with determining the values of k, n and m for any convolutional encoder. So for that one, let's proceed with the representation again. So this is what the connection representation. Let's say this is what one of the convolutional encoder. So in this convolutional encoder, if you just look at here, so k is equal to 1. It means input bit 1 will be accepted at each time and it will give correspondingly 2 output bits. That's why the value of n is provided as a n equal to 2. So overall representation in the format of nkm will be n will be 2, output bits 2, input bit will be 1, and the memory blocks which are actively present in the encoder, that will be 2. Actually, if we look at the equivalent diagram for this, it is showing this kind of resemblance, that is C, B and A. These are the memory we can say the elements or the flip-flops in short. So here in the diagram it is quite clear that it is showing almost 3 memory blocks, but actually in the use only these 2 will be taking active role. Okay, because this C will be used to store the input bit whatever it is coming from this left side. So that's why value of m for this is mentioned as a 2. This is what the format for nkm, convolutional encoder, and this is what the connection representation. Now the constraint length will be based on the value of this m plus additional one flip-flop which we are using to store the input bit. That's why it is 3. So if you just look at the definition of the constraint length, it is nothing but the number of shifts over which a single message bit can influence the encoder output. So here, if the input bit comes from the left side, first shift will be here, then the second will be here, then the third will be here. That's why the constraint length will be 3 for this particular diagram. Let's proceed for the code rate. To determine the code rate, it is nothing but indicated with small r. So code rate is nothing but number of input bits, that is k by n. So for this particular diagram, it is 1 by 2. Constraint length will be nothing but 2 plus 1, that is 3. So total 3 shifts will be required for the bit to proceed. So this is what the constraint length. Now let's proceed with the next thing, that is nothing but the how the approach is explained. Means if we want to write down the equivalent diagram for this particular diagram, then what could be the equivalent diagram in terms of, let's say, the proper arrangement of the shift register considering the input bit. So this is what the equivalent diagram we can say for this diagram which we have seen in the earlier slide. So this diagram can be simplified. This particular diagram means input bit C, that will be accepted over here, and the B over here, and lastly the A, that is over here, and the XOR blocks. So this adder, it will accept the input from C, then B and A. This is how it will be corresponding to the V. So next thing is nothing but to determine the Y, means the second output bit, that is V2 or Y. It is taking from C, then A, and it will be added over here, and the output bit V2 will be considered. This is how the V1, V2, two output bits will be considered for a single input bit.